Thank you. If you could put up the title slide. Again, can I add the thanks of the previous speakers to the organisers for inviting me as a somewhat outlying contributor to this conference. Yesterday we heard rather eloquently put by at least two of the speakers some of the ways in which astronomical technologies benefit humankind and other industries. I'm not going to dwell on that. We heard quick mention of special and general relativity for GPS, satellite motion, astronautics, masers, lasers, and sensitive detectors that are used very widely from medicine to mapping the Earth's surface. There's also less obvious experience that comes from big science in data handling. You remember the story of how the World Wide Web emerged out of CERN and the need to share and work on the same massive data sets. Also, cosmology and astrophysics has a long history of informing fundamental physics in new and completely inexpensive ways, determining limits on the number of new particles, placing the best limits on the possible time variation of the fundamental constants that Professor von Klitzing talked about yesterday. So by using astronomy, you can often do much better than you can in the laboratory because the enormous time travel of light from distant sources to our detectors gives you a sensitivity in time that you can't get just by watching for even a year or two in the laboratory. But I don't want to focus on those applications. Instead, I want to highlight a potentially larger impact of a subject like cosmology. It's an attractive shop window for all of science. It raises ultimate questions. It's a sort of crossroads between physics, biochemistry, philosophy, and theology. And if you stop the average person in the street, you would probably find that they would be rather interested in the sky and the stars. They might be less interested in germanium arsenide and new types of quantum detector, even though they were vital for aspects of their everyday life. So astronomy is a sort of an open door for the public promotion of science. So it has this important sociological impact. And wearing my other hat in Cambridge, I direct, and have done for the last 19 years, a project called the Millennium Mathematics Project. So this was an outreach project set up under my direction in 1999 to inspire the teaching, learning, and appreciation of mathematics and all its applications across the sciences and elsewhere, particularly to young people. And astrophysics is, of course, one of these impressive applications of mathematics. Cosmology tells us where we are in the universe. We'll see in a moment. It also tells us when we are, and perhaps it may shed some light on who we are. It shapes our perspective and our place in the universe in ways that resonate very loudly across the public spectrum. And arguments about the place of humanity in the universe, our significance and our future generally involve discussion of cosmology. Well, cosmology is an ancient speculation. I always say that I don't believe it became a science even until 1915. Only with Einstein's theory of general relativity was it possible to give a mathematical description of entire universes. Einstein's theory permitted that. Every solution of Einstein's extraordinarily complicated partial differential equations describes an entire universe. There's an infinite number of those solutions. Fortunately for us, some of the very simplest and most symmetric solutions describe our universe extremely well. Before Einstein provided that store of possible solutions that describe universes, cosmology was a sort of branch of art history. You could imagine any cosmology you like, and there was no way to gainsay it. But now you have mathematical solutions that describe universes. You can use them to make other predictions and test whether that solution is indeed a correct or a good approximation to the truth. We can't experiment on the universe, but what we do instead of repeatable experiments is that we look for correlations. So a predicted cosmological model will say that if you see one thing, perhaps all old galaxies are red in color, you look for that correlation. So the search for correlations and the statistics that go with it is what replaces experimentation in the laboratory. Well, as I said, fortunately our universe seems to be well described by one of the simplest of Einstein's solutions, first found by Alexander Friedman in Leningrad, St. Petersburg now, and studied and appreciated in great detail, perhaps mostly by Georges Lemaitre, former president of this institution and one of the greatest theoretical cosmologists of the 20th century. I said that the universe is simple. It's almost the same from place to place on the average over its largest scales. It's the same in every direction to a part in about 100,000. So if you like to imagine things, it's like a spherical ball of expanding material. Of course, although the universe is expanding, it didn't begin an explosion. It's not expanding into anything. There's no edge and there's no center. So an old argument about whether we sit at the center of the universe in any geographical sense is answered rather simply by making the point that we can't be at the center because there isn't one. The visible part of the universe contains about 100 billion galaxies, each of which contains about 100 billion stars. So these rather superhuman numbers one perhaps encounters only on Earth when talking about things like the American government's national debt. But for astronomers, they're rather commonplace. Aside from galaxies and stars and planets that we just heard so clearly explained, there's also been a long suspicion that the universe is dominated by things that you can't see. That the dominant form of matter in the universe is in the form of something called dark matter, suspected to be a new type of elementary particle that just takes part in weak interactions, and 6 or 7 times the mass of the shining stars appears by its gravitational effect to be in the form of this dark matter. So millennia of human observation of the sky and the universe has actually avoided ever seeing the dominant part of the universe. In addition to that dark matter, there's also came clear with the capability of our new telescopes and other good ideas 19 years ago that there is another form of repulsive gravitational energy in the universe that goes by the name of dark energy. This might be in effect the quantum vacuum energy of the universe, but it takes up nearly 70% of the total energy density in the universe today. And its effect is to accelerate the expansion of the universe. That acceleration resumed around the time when the Earth was appearing and life was appearing a few billion years ago. So we live in this acceleration era, and the acceleration as we understand it appears to be set to continue perhaps forever, or as long as the universe is expanding. Let me pick on 4 striking things that modern cosmology tells us about the universe that may be of interest to this audience. Although we no longer expect our position in the universe to be privileged in every way, we should expect our position in time to be privileged. And we can understand why we might expect to live at a particular interval of cosmic history, a sort of habitable zone in time. And the reason is because the molecules out of which living and complex things are made that we've heard about from Steve Benner and other speakers don't just spring into being along with the whole of the universe of space and time 13.7 billion years ago. They're made by nuclear reactions in the stars and distributed around the universe when the stars die in supernovae, and some of the elements go back into stars and are reprocessed again. Now, those nuclear reactions that turn primordial helium plus helium into beryllium, and then helium and beryllium into carbon, carbon and helium into oxygen, and so on up the periodic table. These reactions are slow. They take perhaps 10 billion years of stellar alchemy to complete and to make the basic building blocks of chemical complexity in the universe. So we should not be surprised to find that we're living in a universe that's billions of years old. We couldn't exist as examples of biochemical complexity in a universe that was significantly younger. And this carries over into other features of the universe. We shouldn't be surprised to find that the universe is so big. Because it's expanding and it needs to be nearly 10 billion years old, it needs to be at least 10 billion light years in extent. A universe the size of the Milky Way galaxy might have 100 billion stars and planets in it, but it would only be about a month old. So hardly enough time to pay off your credit card bill, let alone evolve complexity and life. There are further byproducts of this huge amount of time that we need for complexity to get going. When you expand things a lot, they tend to get dilute and their density falls. The universe, to a first approximation, contains nothing. It's almost empty. If you smoothed all the material out in the universe into an evenly spaced grid of single atoms, there'd be about one atom in every cubic meter. There's no laboratory on Earth that can make a vacuum that's as empty as that. So if we gather those single atoms into planetary-sized objects, you run into one every 10 light years. If you gather it into stars, it's every 1,000 light years. Into galaxies, every 10 million light years. So the enormous sparsity of material, the huge distances to other worlds, is a consequence of the long time and the great amount of expansion. And one of the other consequences of that expansion is the temperature falls. The amount of radiant energy in the universe is extremely low. And so we shouldn't be surprised to see that a universe which is suitable for chemical complexity has to be both big and old, dark and cold. A recipe which, for someone like Bertrand Russell and philosophers of progress in the early 20th century, would have been completely different to what they were advertising about the state of the universe. Well, as we look back to the early stages of the universe, there's an idea about the universe which has become the central theme of modern cosmology. And it's a theory called inflation, and it attempts to explain a number of the large-scale features of the universe that otherwise seem to be extraordinarily improbable. That smoothness and isotropy, the special rate of expansion that the universe displays. And the idea of inflation is simply that there was a very brief interlude of expansion early on in the universe where there was a surge of accelerated expansion for a finite time. And that surge was enough to endow the universe with those special large-scale properties. And we also hope that if we look at this picture here, the idea is if you imagine the early universe divided into little regions just big enough for light to travel from one side to the other, then this surge of expansion allows one of them to have expanded enough to encompass our whole visible universe by today. Without the acceleration in the early expansion, ordinary expansion would not be sufficient to achieve that. And so this idea can be testable because the little bubble that ends up encompassing our whole visible universe contains specific quantum fluctuations. And they are inflated as well in this process, and we can test whether the fluctuations we see today follow the statistical form predicted by that idea. Well, this idea has significant observational support by examining those fluctuations, but you can see from this cartoon that there is also a philosophical dimension, that if this tiny fluctuation here accelerates to encompass everything that we see, what about the fluctuations that are beyond its boundary, out of causal contact with it? They must inflate by different amounts or not at all. And this is the first time there's been a positive prediction that beyond our observational horizon in the universe, about 42 billion light years away, we should eventually expect to encounter completely different structure in the universe, perhaps different aspects of fundamental physics, mirroring the differences in the different little regions beyond the horizon early on. So if you thought geography was complicated when you were at school, it's much more complicated now. And worse still, history has become more complicated than when you were at school, because this process has a temporal analog. This inflation, once it starts, never ends. So we expect that tiny regions within each inflated bubble then undergo further inflation, rather like a self-reproducing disease, and spawns many, many sub-universes indefinitely into the future. So we see ourselves inhabiting one of these little regions within this self-reproducing process. If we follow it back in time, it may or may not have a beginning. If you think about the whole network, our individual bubble, our visible expanding universe, will have had a beginning. Both processes don't appear to need to have an end in the future, though there's no indication of that. Well, what about the future? Some people worry a lot about the future, but you would have to be a big worrier to worry about the cosmological future as opposed to the future of the Earth. I said earlier that our universe accelerates today, and we don't know any connection between this very, very early acceleration that we call inflation, that comes to an end, caused by particle physics processes, and the acceleration we're participating in today. They may be linked. It may be that today's acceleration is another edition of this self-reproduction in some way. But if we look to the future, at the present time, the separations of the markers of the expansion of the universe today, great clusters of galaxies are the smallest markers. Everything else is held together by stronger local forces. They're expanding exponentially apart in time. And we have a pessimistic long-range forecast that eventually all the stars will die. Some bigger ones will turn into black holes, but they will eventually evaporate to some relic perhaps, or to nothing, by Stephen Hawking's black hole evaporation. So the universe is destined to become a great cemetery, a sort of cosmic cemetery of dead structures. But the discovery of the acceleration of the universe has added another rather remarkable ingredient to this long-range forecast. Because of the acceleration, what is created around us is a static communication barrier. So at the moment, the distance away from which we can receive light signals gets a little bit bigger every day, by one light day. But when the acceleration completely takes hold, there is a fixed horizon. And after about 100 billion years, its effects will have become really quite dramatic. All the distant galaxies that we see by the Hubble Space Telescope and other instruments will have expanded away and passed out through that fixed boundary. We will never see them again. If there are observers of the universe in that far distant time, they will not be able to see any of the things that we can see today. They will not know that there are other galaxies. They will not be able to determine the existence of this dark energy that's responsible for that state of affairs. So in a sense, the study of the universe as we know it today would become a branch of literary history, available just through old copies of the Astrophysical Journal, or books written by Lord Rees and others. This is a sobering state of affairs, in that we saw earlier that there is a time before which we would not expect life, complex life, to exist in the universe, because the building blocks were not available. After the stars die, perhaps we wouldn't expect life to be able to evolve for the first time. But this shows us there is also a much longer period during which it's possible to study and understand the universe. That won't always be possible in the way that it is today. Thank you.